20-minute talks apiece. I'd like to turn this over now to Michal Balazia. Let's see if I can get you presenter.
Hello.
Let's get your slides up, and Michal is.
Yes, let's see if it works.
While you're doing that, I'd like to introduce Michal Balazia. He's doing some really important work on use of video. I originally met Michal at the ACM Multimedia in Australia, a year ago. You know, use of video may very well prove to be one of the important means that we can help people learn how to be more civil, courteous, tolerant, and respectful when trying to talk to each other and listen to each other. So I turn it over to you, Michal. Please, please present your slides. And are you able to screen share there?
Hello. Yes. Thank you for a nice introduction. So,
is anyone seeing Michal's slides yet?
Can you see my slides?
No. It's so I double checked that you should have presenter, but it's not showing.
I will try again.
There we go. Okay, and then full screen if you can get it into full screen. Yeah, excellent.
Okay. Can you see it now?
Good. Well, it was there momentarily and then it disappeared.
Okay, I guess it disappears after if I try to put it on the full screen. So I will just share it like that. Is it okay? Okay.
Let's have at it.
Yeah. So Michael, I'm gonna be speaking about artificial intelligence, and there were a couple mentions about AI today that were showing it a little bit as a dangerous technology. So I hope I will show it in a better light now. So I am a permanent researcher at INVIA Sophia Antipolis, which is down here in the southeast of France. There, I'm a member of the STARS team, which is a team which does mostly artificial intelligence for video. And I'm also part of the COPTECH team, which is the medical team at the Nice University Hospital. Here are the two pictures. So in the left, is the picture full of doctors, full of psychiatrists who do bipolar disorder, schizophrenia, Alzheimer, PTSD, and so on. Also for children, the autism spectrum disorder. And in the right side, there is the computer science team that where is my office. Yeah. My slides are much slower now with presentation. So considering general human behavior, okay, we are trying to measure the human activities objectively, not only the activities and actions, but also the emotion of people, eating habits and lifestyle, and that's all for the purpose to improve the quality of life people. Also people in general, but more specifically people with the behavior disorders or with psychiatric disorders. For that, we use different methods, but they all have the common denominator, which is their vision systems. They're based on computer vision, and sometimes we add additional modalities, but the vision is the most important one. We try to recognize human activities, and our models are typically trained on large number of data sets. Also, there is a large variety of sensors, not only video cameras that are classic, but there could be depth video cameras, or that could be a microphone. There could be physiological signals recorded by a wristband, and so on. Our applications are in safety. So, for example, in security in the street or in the airport. For health, that would be the psychiatric disorders, and generally well-being, that would be when people need some assistance in their life. We are trying to provide solutions also for that. There are more other applications that are not that important for us. For example, sport, but this is just for us to check if the methods are working. So typically, I will now present a couple projects that we do in our team, and some of the topics are really hard, and I can show you roughly what's our solutions. So we do people tracking, multi-object tracking. We do it with a grounded Dino as a foundation model, and then segment anything, which is a technique for foreground to background segmentation introduced by Google, and then track anything, which is there are three modes of this tracking anything, also introduced by Google, Qt, Diva, and Masa. In this problem, we typically segment the foreground from background. Foreground are the selected people that we want to track, and then background is everything else. So if I just play this video, we just care about the selected people that are our foreground, and the task is to correctly track them. This is actually the topic addressed by my colleague, PhD student Tomasz. He does multi-object tracking in various environments. For example, this is in the street. Here, all the people need to be detected and also tracked. Not only the detection is important, but tracking here is very important because we need to not only just have the rectangle around these people, but also they need to keep the correct and non-changing identity number. So a good measure of success is that that people would have an unchanging ID number over them. Tomasz also applies it in sports, culture, performances, and this is just another view of the street. As a problem of this is person re-identification. So when you have, this is for security application, when you are interested in tracking a particular person, in this case there is a lady with a suitcase. She's wearing a red jacket, and you're interested in searching this person in various video cameras. So she's wearing the same thing all the time, but you can see her from different angles and also from different distances. Now, more technically, we typically feed all of those images, all of those appearances into a neural network. A backbone is typically given, which is classic feature extraction. Backbone, in this case, it could be ResNet 50. And then each of those viewpoints is encoded separately. Classically, for person identification, people use cross-entropy loss, but we also introduced the triplet loss, which is defined up here, is to minimize the distances between the individual appearance of the same person and maximize the distances that would be appearances between different people in the images. This is a work of my colleague Hao. He has some very nice successful cases. For example, it was very difficult to recognize people from different distances, but also there are some failure cases. For example, when there is occlusion or people wearing similar clothes. But even the system was surprisingly correct, which discovered some annotation errors. So it was correct when actually the human annotators thought that this is a different person. So this technique actually fixed some annotations. We typically do it with masking and data augmentation. So we first mask the face so that we disregard the person's face, so that the face is not used for recognition here, and then we do some kind of augmentation. First level of augmentation is we just flip the picture and also remove something in the middle, that would be used for carrying objects. And the second type of augmentation is cropping, changing colors, and cropping and changing colors. For that, we create a model, the representation that is invariant to perturbations, which is exactly, we created those perturbations. Now the model is much more stable. Now, my colleague Snehashi, he is doing weekly supervised video anomaly detection. So there are plenty of anomalous activities happening in the video, and also for the security, we need to detect specific anomalies. But the problem with this is that we have lack of annotation. So typically, there are not many people working on annotating the data, so we just don't have it. Second is that the anomalies are human-centric, so the anomalies happen when there is a bad actor, some person who is doing something dangerous or malicious. For example, here is a shoplifting. Another problem is that the anomalies are sparse. That is, you have the whole video of perfectly fine situation, but only on a very short moment something bad happens, and you need to detect that. And then you have long and short anomalies. So typically, long anomaly here is a guy stealing a motorbike. It takes very long time until he really steals it. And the short anomaly here is just some kind of accident where the bus runs into a crowd of people, and this is just a few seconds. I could explain the AI structure here, but I can only say that as an input to this structure is that we feed it with the perfectly normal videos where nothing anomalous happens, and also we feed it with videos which are almost perfect, but there is some kind of anomaly, typically very short anomaly in it, and we're trying to distinguish these two types of videos. So this is a crucial point in our architectures, that normal videos and almost normal videos, and we try to distinguish between these two. RGB features are typically very strong, but we try to also extend the architecture with human pose, depth, panoptic masks, optical flow, and text, and this constitutes a large vision language model. This model also understands the human questions and is able to provide some interpretation of the reality there. So if you ask for abuse, the model is able to describe the reality captured in the video by words. We also do activity recognition for daily living. So not only for security, but also just normal daily life activities. For that, we have a Toyota smart home dataset. This is recorded at people's houses where they just normally live, and there are plenty of actions that they perform. For example, walking, drinking, reading book, cooking, and so on. Of course, we use multiple modalities: RGB, audio, text, biosignals, EEG, ECG, EDA, heart rate. This is an example. I can try to play it. This is an example of video. So left column are correctly detected actions. Middle column is wrongly detected, and the right color is misdetected. So this is just a demo with a skeleton over the person's body, trying to figure out what is going on. So green means perfectly fine, that our system is perfectly fine, and then there are two types of error: wrong detection and misdetection. Not only for normal life, but also for autism spectrum disorder. We have PhD student Abid. He just finished his PhD. Typically, kids with autism spectrum, they have deficit in attention. They don't have deficit in attention, reciprocal interactions, and communication. And of course, they have restrictive, repetitive behaviors and interest. Typically, they when they are interacting with other people, they dance, they shake their hands, and with the depending on their severity, they sometimes don't even speak if they have severe autism. So what we are trying to do, we are first observing a lot of those interactions between children and also young teenagers. We observe tight interactions, conversational interactions, and loose interactions. The problem here is to take untrimmed video where the kid is in a room with some psychiatrist, and we try to detect all the actions that they do during that interview, and then predict a severity score of their autism. Of course, we do it in our way, as we do the anomaly detection. So autism behavior is, in our understanding, an anomalous behavior. So of course we trade the data set. We trade the model with perfectly normal videos and also with videos where some anomalies appear. Now, my student Valeria, she's now working on Stress ID, which is a data set on stress. She's also measuring physiological signals, and she's trying to recognize emotions from facial expressions. The data set looks like this. These are people from our team. Yeah, we have some demos. So we also measure the gaze and try to figure out their emotion during a scripted interaction. Now, my personal project is Mephisto, which is detecting psychiatric disorders from multimodal data. So imagine a person having a problem, some psychiatric problems. Think of bipolar disorder, PTSD, or schizophrenia. They come to see a medical doctor, a psychiatrist, and they are having some kind of interview. That interview contains unstructured, spontaneous speech, some subtle action and facial expressions, emotions. But that room can also be equipped with some technology that can be observing the interaction and can help the clinician to better diagnose the patient. Not only the better diagnose, but also to have some kind of clinical tool that would provide some reports, some analysis after each interaction, after each interview, and the clinician would be able to have a conversation, something like with the ChatGPT, with that system, to figure out into a bit better detail what the patient is up to. Of course, this is not just a ChatGPT. This would be, of course, trained on clinical data, so it would not be just a typical text model. Of course, it would be collecting video data, so just like recognizing emotions and gestures, but also the physiological data such as heart rate or skin conductance, which could be very useful at analyzing symptomatic behavior. This is a screenshot from that dataset. So we have clinician and a patient, we have biosignals, and we are trying to detect plenty kind of behaviors. Already without watching that video, we should be able to see that, let's say, clinician, the brown marks here and the patient, the green marks here is the clinician has strong eye contact and the patient does not have a very strong eye contact. Actually, the patient is actually avoiding clinician and is actually more comfortable when the clinician is not looking at the patient. So this is something that you can already see from the analysis here. Of course, the analysis can be more targeted and designed based on what clinicians desire. Okay, so just to conclude, we develop global frameworks for building real-time video understanding systems. Our activity monitoring systems are measuring various types of features from handcrafted to unsupervised learning models. We would like to have a robust and long-term video monitoring, and ideally online, but sometimes models are too big, so online cannot be always guaranteed. We want to have a viewpoint invariant representation of reality, so doesn't matter from where you're looking at. We want to have unsupervised model because supervised is very difficult to have. You need to have annotations, and that is in current realities almost impossible. And then we want to have generic semantic activity models, which is the models that can understand pretty much everything. So think of it like generic AI. We try to analyze emotions, fine gestures, head posture, facial motions, and all of that can be very fine and nuanced. All of that can have hidden meanings, and that all can correlate with mental states. We of course have different multimodalities, and one thing to consider for us in the future would be to get some feedback from that model, so that the model is communicating with everyone involved, and that will be reaction to simulation, and we're developing serious games for that kind of experiment. Thank you for attention, and I can answer questions if there is some time.
Thank you, Michal. Wonderful overview of all the incredible work that you're doing there with your group. Because we are behind schedule, let's defer any questions till we get through all the tech talk. So please stick around, Michal.
Okay.
I For those who don't know, I am a psychiatrist, and most of my clinical work has been in emergency and forensic psychiatry. So I will just make the one remark. I think your greatest challenge is going to be dealing with what we call the players, because players are master manipulators. All right, I'll leave it at that. Let's move on to Kento.